Hi everyone, Professor Hyman here, IBUS 620. We're going to talk today about notation. And we haven't studied all of these concepts yet as I make this video, but I think it's important for you to know the basic conventions of the notation we're going to be using. And there's a couple of real simple rules. In general, you want to realize and understand and internalize deep in your gut that capital letters, whether they're Greek letters or Roman letters, are population statistics or population attributes. And lowercase letters are related to the sample. Okay, now there are some exceptions, but in general, this is how it goes. Okay, now let's start over here. I've called this lecture Notes on Notation, and going to just point this out, and then we're going to talk about the population notation first. And what is the population? Let's start with that. It's something we want to say something about. We want to say something about a population from a sample. So a population is everybody, and a sample is a small group of folks from that population. And what do we want to say when I say we want to say something about a population from a sample? We want to say the truth. We want to get at the truth, okay? Now, that's all. Another way of saying that is that the information that is represented in the population is reality, but the truth here is it's rarely known. We rarely know this stuff, but we estimate it, and I'll come back to that in a minute. So mu, the Greek letter mu, mu, is the population mean, and we rarely know the population mean. We sometimes do, and there's a topic later in the class that covers when we know that. And then sigma, this is actually a small sigma, so it's a little bit of an exception to the capital letter rule for populations. Sigma is the population standard deviation, and as we'll cover in another lecture, it's equal to the square root of the quantity of the sum from I equals 1 to n of xi minus x bar squared, all divided by n. Notice that's an n. I have a whole video on the difference between that and the standard deviation of the sample. Okay, I'll come to that in a second. But first, we also have this other quantity, which is called the population variance, which is notated sigma squared. It's rarely useful. It's often an intermediate product because the units don't make a lot of sense. There's no such thing as square dollars, for instance. But we all know what dollars means. So, but sigma squared is simply the same as sigma, except without the square root, obviously, since we're squaring it. Okay, the square root goes away. And then capital X sub I is an actual real datum or data point, if you will. All right, now let's contrast that with the sample notation. Okay, and just to recap, the sample is used to represent the population in our calculations because usually populations are large and they're very expensive to get the data from a population. You have to get everybody. You can't have any missing data if you have population data. So it's much more convenient to get a sample from a population. And now here's the notation for the sample. X sub I, small x, lowercase x, is sample data. Okay, x bar, small x, is the sample mean. That contrasts with mu over on the population side, and x bar is the sum of all the x's that you have divided by n for a given type of data. So if you've got a whole bunch, if you've got 30 people's age, then you add up all the ages and divide by 30. Okay, that's all this notation means. Okay. The standard deviation of the sample standard deviation is notated by S, and S is similar somewhat to the sigma calculation. It's the square root of the sum of the deviations from the mean squared divided by n minus 1. And it's n minus 1 in this case, not n as we had it over here. I have a whole video that explains this in another part of the course. It's an interesting reason. I'm not going deep into that now. Let's just keep going with the notation though. S squared is the sample variance, and S squared is simply the standard deviation squared. So again, the square root goes away. This radical is dropped, and you have just the sum of the deviations from the mean, the xi minus x bar quantity squared over n minus 1, not n. And again, I have a video on that topic. So that's the basic notation, okay? Let me now jump ahead a little bit to a slightly more complex aspect of the notation, which is how this notation plays into the regression equation. And we have this idea of a linear regression equation that there's these in the population. I'm coming up here now. In the population, which is, again, all this is reality, so the outcome, the dependent variable, is equal to the actual effect times the actual data value, plus if you have another variable, let's say this one's age, data is age, this one might be gender, and then there might be some other ones, you know, attitude towards ice cream, something like that. But the point is that for every variable you have, and this is the independent variable, which I'm abbreviating IV, okay, you have an effect which is weighting on the independent variable. So this is the real effect, and this is the real value of the data, neither of which we know. We're guessing at those by virtue of having a sample, and we're making an intelligent guess, but we never actually know for certain. Okay, and I'll come back to that in a second. But let's jump down to what this equation looks like. And again, now you've got the dependent variable capital Y of I, Y sub I, is equal to beta 1 x1 plus beta 2 x2 plus beta I xi. That's the last independent variable, plus a constant. Okay, it's linear, so there can be a constant. The constant could be 0, but we make room for the constant. We don't really care that much about the constant, but don't forget about it. The sample, it's very corresponding now to the population. Okay, only we're using lowercase letters and we're not using Greek letters. So small y sub I equals small b1 times small x1 plus b2 x2 plus, and I missed some dots here, plus dot 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 plus bi xi plus the constant. And here what we've got is the sample effect on the independent variables that we measured. We actually measured these. Up here we didn't measure these because we can't, but those are the actual data values. We didn't measure the beta 1, which we really want to estimate. So and that we estimate it by B1. So beta 1 in the population corresponds to B1 in the sample. And so now we can say that the point of regression is that regression calculates the BIs, the B sub i's. The BIs are estimates of the beta i's. The BIs are estimates of the actual values of the weight that you give, the power of the effect, the strength of the effect on the independent variables which you have measured. Okay, so the BIs are the goal of regression, is to calculate the different effects of the different variables on your outcomes. Okay, so again, regression calculates the BIs, and the BIs are estimates of the beta i's. The beta i's are reality, which we never really know for certain. We just estimate through the regression equation. Via the BIs, we estimate the beta i's. Okay, now this will become clearer as we move farther into the material later in the semester, but for now, the key thing to be familiar with is probably the first two concepts I talked about, which is the notation for population and the notation for samples. And then the regression stuff, we'll come back to that later. But for the early parts of the class, you want to make sure that you know the difference between the notation for population and the notation for sample. That's it for now. I look forward to our next video. Thanks for watching.